Okay, welcome back to our AstrotWin course. Where we have the workshop with Christina right now. So, Christina, it's your time. Go on.
Yeah, thank you, Pablo. I'm gonna share my screen now. Okay. Okay, so this week we have been working in the measurement of the clustering of a galaxy catalog. Then during the first workshop, we just download a catalog and we were playing a little bit with the catalog. We were making some plots. Yesterday, we started with the measurement of the clustering itself. This is the workshop number 2 that we were following yesterday. I was doing all those steps together with you. And we were here in point number 8. At the end of the workshop yesterday, I was explaining you how to compute the DD term. Then I explained you using this worksheet. I was very detailed. Then I hope you were following this. But we didn't have. I didn't give you so much time to really code this by your own. Then today we are gonna finish working on this part of the workshop of yesterday, and after that we will move to continue with the workshop number 3 that you received in your email. Then I already explained you how to measure DD. Then I'm gonna show you what we told yesterday. I will repeat that I'm an IDL programmer. Then you don't have to follow my syntaxes, but you can follow the idea. And yesterday I show you, or I explain you how to compute DD in terms of code. Then I told you that there is one inefficient way to compute DD, in which you have 2 cycle force, and you are computing for each step. You are computing the distance between one individual galaxy with another individual galaxy. Then you can follow this way if you want, but I also said that the more better option is this one here, in which you only have 1 cycle for, and you compute the distance between one galaxy and the array of all the other galaxies at once. Then I will comment this part here, and I will be working on this right now. I'm gonna write the way in which I can compute DD here, and then I will give you 10 minutes. Then you can code it by yourself or continue what you started yesterday. Then I hope this is clear enough. Maybe I will increase a little bit the size. Okay, I think that is better now. Okay, so here I just create a cycle 4, which goes from the first position in the array of my data and goes until not the last one, but one position before to end the array of the data. Then I just put here in the comments what are the steps that we have to make here in this cycle 4. Then the first step is to compute the distance between the galaxy with the position I, in which I am currently, and all the rest of galaxies below that position. That means that I have to compute, I have to take a sub-array starting at the position I plus 1. to do that, I have already some coding here, so I can do this more faster. This is just the function in IDL who compute these distances on a sphere. This is called G-circ because this compute distances in a circle is called. Then I'm just providing the coordinate of the galaxy, the array ascension and declination of the galaxy for the low mass catalog. In this case, it doesn't matter if you start with a high mass catalog. And I'm also providing the positions of the rest of the galaxies, starting the position I+1 until the end, the array ascension and declination. And here is just the parameter in which I receive the distance in arc seconds. Here I'm just, this division by 15 is just because this receives certain units. And then I have to make a conversion, but you have to check what you have to do in your case in Python. After I compute the distance between one galaxy and all the rest, I have then to check what is the position in the binning in which I have to increment 1 in the DD array. Then for that, you have some options. One of those is like the inefficient way, but it's still okay if you know the limits of your binning. You can use like just an if-else rule in which you can check if the value is between this and this one, then you have to increment 1 at this position. You can do that if you don't have so many bins. In this case, we have 7 bins, then you could do that. But the way in which I do this is using just like an equation to compute the position within logarithmically spaced bins. Then this is just an equation. It's basically, I'm using this definition. This is the logarithmic of x, which x is the distance that I am getting. I have to subtract the logarithmic of the minimum value of the array and divide all that by the bin size, which is different for each bin, of course. Then that is what I'm doing here. This is logarithmic of the distance that I just got from the function before. I subtract the logarithmic of the first position in my array, and then I divide it by the bin size. For some reason, I mean, I think that we computed the bin size before in the code, and you could just divide by that bin size. But here I'm computing the bin size again, and that is why this looks like this. What else? Yes, and that's it. And here I'm increasing 1 because if you remember, I choose DD to be a little bit larger because I also storing the distances in the position lower than the minimum beam and higher than the maximum beam. Then I include 2 extra beams in my DD just to have more complete information, but you don't have to do that. And if you don't do that, you don't have to then increase 1 here. If this is too complicated for you, or you don't understand this way to compute the position in which the distance is located, you can, as I said, just make this with an if-else conditions. Okay. Then here, I'm storing the position in the DD array, in which I have to increment 1. And then the next part is basically make, yes, I make a cycle 4 here to add 1 at each different position of the DD array. Then I go through each of the position that I got, and for each position that I got, I put that value. This is J. In the array DD. Then at DD, in the position, I'm gonna increase in 1. And in IDL, it's always better to say that this is a double. Yeah, and that's it. In general, you don't have to do more than that. In my case, and just because I have 2 extra bins in my DD array, I have to actually make here some extra lines in which I'm checking if the position is higher than my last bin or lower than my lower bin. I assign them the position of the first or the set or the last position in the DD. Then that is not necessary if you're not doing that, but I will just put that part here because that is the way in which my code works. Then I will put this part is only because this part, this 4 lines is just to store the number pairs in the very first and very last positions, but you don't have to do that, as I said. Yeah. And that's it. Then that is the way in which you can compute DD for your array. I think I ask you to plot this. In the number 7, I ask you to plot a log-log, to make a log-log plot of theta begin versus DD, just to check that the result makes sense. Then I have part of the code for the plot here. This is just to define the plot in IDL. And I'm gonna plot, in this case, is theta begin between 0 and -2, because the last value of theta begin is the end of the last bin. Then I'm not plotting that that position. And DD, and in my case, this goes from the position 1 up to the position 2, because my position, in my position 0, I'm just storing the number pairs that I have below the minimum, and in the last position, I'm storing the number pairs higher than my maximum value. Then I'm just plotting what we are interested in. And this is just to define some parameters of the plot. And I'm gonna ask to plot this in logarithmic scale, like this. Okay, then let's see. This will take a little bit of time because this have to compute all the distances. But I'm gonna run the code here. And now this is computing the distances for the 10,000 galaxies. Great, and I have a mistake in the plotting. Where it is? Yeah, it's just that. I would just make this run again. You can see that even when we have 10,000 galaxies and we are computing the distances between all of them, this doesn't take so long time. Then that is not bad. Okay, now it worked, and I'm gonna check the plot. Yes, this is my DD plot. Then this is the theta value, and this is the DD value that I have for each different bin. This is in logarithmic scale in both axes. Then this is more or less what you should to obtain. Great. Then I'm gonna give you 10 minutes to finish this part, to work on this. I think in 10 minutes you can finish this. I'm gonna also upload this code in my webpage. Currently, the code is uploaded, but it's the version that we did yesterday. Then I will update that, and in 10 more minutes I will be back, and we will start with workshop 3. If you have any question in the meantime, just feel free to ask. Okay, I'm back now. I hope that all of you are following me. If you think I'm doing this too fast or too slow, please let me know. Then I can try to be slower or faster. You can say that in the chat or something. Then now I'm gonna assume that you are following what I'm doing. I'm gonna share my screen. Okay. I already uploaded the result that the code that we just finished for workshop 2. Then you can find it in the web page, which is this one here, and also included the plot of the DD vector. Okay, so we are almost done with the computation of the clustering. Then for the workshop today, we will finish this and to obtain the nice plot of the angular correlation function as a function of theta in this case. Then the first point, if you finish the computation of DD, then you can now easily compute the term RR. The term RR is basically the same things, but the only difference is that you have to provide the random catalog instead of the data catalog. Then to generate RR, we first need to create an array with the same length as DD, and we will call this array RR. And for the computation of RR, yeah, here is I'm saying that we have to repeat what we already did. You can download from here the code that I use and the plots. And I forgot to provide you the DD values. Actually, then maybe if you were not successful to create DD, you can just create by hand use the same DD as me, and then you can try to reproduce this. Then this DD value, I'm gonna put this in the workshop for today. Then this is the workshop number 3. Then this is a different code that the one that I upload in the web page. But this first part is just a copy of what we did. Then I just read in the catalog. This is the clustering parameters, the definition of the theta vector, the creation of the DD, and this is the code that we just created together. Then I just copy this in this part of the new code. Here, just after the computation of DD, I put the values of DD that I obtained. Remember that this first value, we are not going to use this first value because by definition, I just storing the number pairs at smaller separations, and the same with the last value of DD. This one is just for my records, but you don't have to use them. Okay, so for the computation of the RR, we have to repeat same thing. Then I'm gonna create the RR vector, the same dimension as DD. Then I'm gonna define NR as the number of elements of my random catalog. This is my random catalog, which I already read here. I read the random catalog, and then I store the coordinated, the right ascension and declination for the random catalog in those variables. Then I'm just using those variables here. And now, to compute RR, I'm gonna just copy the code that we use for DD is exactly the same code. Then here, the only difference is that the variable have to go until the end of the random catalog, and I want to change just the name of the variables. Then here, the coordinates for the distance is the one corresponding to the random catalogs. It's just some small changes. And that's it, I think. Then here I compute the position, the same thing that we did before. And then here also, this is not DD, but is RR. And that's it. Then this should be, should make the job. Then, as you know, as you see, it's not so much work if you already created the vector DD. Then I ask you to make a log-log plot of theta versus RR just to check our results. Then I'm going to plot this here. Again, I have this prepared from before. And this is just to open the file in which I will store the plot. And I'm going to plot theta begin. Again, in the positions from 0 to -2, but that depends on how you created your vector. And RR goes from 1 to -2 because the same reason as for DD. I'm just defining the type of point. This is RR. I asked to make a logarithmic plot. Okay, that should work. And I'm also gonna print here the values for the RR. Then I can provide those values to you, and you can try to reproduce the values. Okay, let's see if this works. This gonna take a little bit of time because now we are computing DD and RR, and we have to measure all the distances. In my case, this is not taking so long. You see less than, I don't know, like 30 seconds or something. Okay. This here are the values of the RR, but before to provide you the values, let's go to check the plot. This is workshop 3. This is the plot that I just created. Here we go. Okay. This is how your RR plot should looks like. Then this is just theta, the beginning of each bin, and the number of random pairs that we found. We can compare this with DD. Remember that the number of objects in both catalogs is similar. Then when the code works well, we can increase the number of sources for the random catalog. But the trend is kind of similar. It's actually hard to compare here, but in the next step, we are gonna compute the ratio between those two things, and we will check if we have any clustering signal, actually. Then here are the R values that I got. I'm gonna print this here. Then when I upload this into the website, you can check that you are getting the same RR values as me. Okay. Then now I will give you.
Cristina, there is a question, I think. Armando Lara. Okay.
Yes. What is the fastest or best language program to make this type of computation? Well, I don't think there is a specific language. I think it's more related with how efficient you can make the code. But I think that in IDL or Python is equally good in terms of time. Probably, yeah, Python or IDL is perfectly fine. I think it's more related in the way in which you are coding. Of course, if you compute the distance one by one, is slower compared if you compute the distance with an array. Also, when you check what is the position in the beginning in which you have to increment one each time. As I show you, I'm just using a formula for that part. Then that is pretty fast. If you make this using if else and checking if the distance is in each one of the position, of course that will take longer. But yeah, there is not like a special language in which this is faster or slower. I guess that in C, C++, you have less libraries previously defined, and then that will take longer if you have to make the code for everything. Okay, then I'm gonna be here if you have questions, and I will come back in 10 more minutes. Then you have time to also make your codes and compute the RR and try to reproduce what I got. Okay, I'm here again, and there is only one more minute left before the break. Then I think that you can continue working on this, and I will continue with the rest of the workshop in 15 more minutes. Then at 11:30 your time. And yes, we are almost there. Just one more step before to compute the correlation function, the more basic form of the correlation function. Then I encourage you to work in your codes and to wait until the next part of this workshop.
So thank you, Christina, for this first part of the workshop, and see you in 15 minutes. Okay.
Yes, great. Bye.
Okay. We'll be back. Bye.